right, guys. So this is part two of the going over the 2015 chemistry SOL. Um, on part one, we finished on question 17, and now we're just going to pick back up at question 18. Okay. So which of the four substances on the pH scale are slightly basic? So remember, basic means a pH above 7. So slightly basic would be slightly above 7. So the human blood is slightly basic. Whole milk would be slightly acidic because it's slightly below 7. Lemon juice would be kind of very acidic, and calcium hydroxide would be very basic. All right, so human blood there. Okay. Which element will most likely form covalent bonds with fluorine? Okay, so remember, covalent means nonmetals reacting with nonmetals. So um, just look for another nonmetal. So we go to our periodic table. Whoops, not that one. Yeah, that one. Okay, there we go. And notice what we have. Let me just go back. So potassium is here. That's a metal. Remember, on the periodic table that you have on the online SOL, there you have your bold staircase here. But at the bottom of it, it has an arrow this way and an arrow that way, and it says metals are this way and nonmetals are that way. So if you forgot that the majority of elements are metals and they're on the left side of that bold line, and the nonmetals are on the right side. The one exception is hydrogen is not a metal, it's a nonmetal. But everything else over here is considered a metal, and everything over here is considered a nonmetal. And so for potassium, that's a metal. If it reacted with fluorine, that would be ionic. Okay. Neon is a noble gas. It doesn't react. Okay. So remember, these guys don't react. So you want to pick a nonmetal, and neon is a nonmetal, but you want to pick a nonmetal that doesn't have a noble gas configuration, electron configuration, because those don't react because they already have the right number of valence electrons to be stable. Okay. And then tin is another metal. If you didn't know where it was on the periodic table, it's Sn. It's right here. So it's a metal. It would be ionic with fluorine. So that leaves us carbon. Remember, carbon's a nonmetal. Carbon would form covalent bonds with fluorine. Okay. The physical process of evaporation involves, okay, so evaporation is a type of vaporization, which means liquid to gas. And in order for particles to escape to the gas phase, they have to overcome what we call their intermolecular forces. If you remember, like water has hydrogen bonding, there's dipole-dipole interactions, there's London dispersion forces. You don't really have to know all those differences in IMFs and that kind of thing, but just understand when you melt something, you're breaking IMFs. When you vaporize something, you're breaking IMFs. When you do the opposites of those things, IMFs, intermolecular forces, are forming. Okay. All right, so how many moles of O2 in the chemical equation when balanced using the lowest whole numbers? Okay, so it's just balance the equation. And so when you balance the equation, the coefficient for oxygen is 3. Okay. All right, so before we even do it, just cathode ray tube. J.J. Thomson discovered the electron, right? Rutherford, gold foil, discovered the nucleus. Dalton had an atomic theory. So as soon as I see a cathode ray tube, I'm looking for electron, I'm looking for J.J. Thomson, right? That's probably one of the answers. Let's see. Okay. Yep. All right. So this told us that J.J. Thomson did this, and he gets credited with discovering the electron using the cathode ray tube experiment. Okay. So that's just one of those fun facts. You either know it or you don't. Okay. All right. So the Haber process, it doesn't matter if you know what the Haber process is. All it is the synthesis of ammonia from hydrogen and nitrogen. So this is the balanced equation. And this is kind of a lot going on here. You had to come up with this balanced equation, okay, so that you know that hydrogen and nitrogen react in a 1:3 ratio, okay? And so you want the right stoichiometric quantities of reactants. So that means for every 1 nitrogen, you need 3 hydrogens, okay? So here we got 1, 2, 3, 4 hydrogens. We got 1, 2, 3 nitrogens. That's not the right ratio. So here we're just counting. Now, we don't have a picture where it's 1 of these and 3 of these, but we do have the picture where it's 2 nitrogens and 6 hydrogens, and that ratio reduces to 1:3. So this is the correct stoichiometric ratio. Stoichiometric, remember, think coefficients, think mole ratios, balanced chemical equation, that kind of thing. All right. So remember, there's two ways to make something boil. You can either heat it up so that its vapor pressure equals the atmospheric pressure, which is usually 1 atmosphere, or you could lower the pressure above liquid, and therefore it would boil at a lower temperature. So this one's just asking you to kind of understand what the definition of the boiling point is. The boiling point is where the vapor pressure equals the external pressure. So you can either heat up a liquid to make its vapor pressure equal to 1 atmosphere, which is normal atmospheric pressure, and that's the way we normally get things to boil, or we could lower the pressure above the liquid so that its current vapor pressure is equal to the pressure above it, and then it would start to boil at a lower temperature. Okay. According to the periodic table of elements, which elements belong in the same period? Remember, period is the row, and group or family is the column. So same period would mean same row. So like hydrogen and helium are in the same period. Sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon, they're in the same period. Group is vertical, so fluorine, chlorine, bromine, iodine, they're in the same group, but sulfur and chlorine are in the same period, right? That's what we're looking for. So same period, and it's weird, but you just have to figure out like germanium, arsenic, gallium. Let's find that on the periodic table. Germanium, arsenic, and gallium are right here, right next to each other in the same row of the periodic table. Okay. All right. So here we just have a quick mole conversion. We have particles and we want moles, so we just divide by Avogadro's number. Okay. No stoichiometry here. It's just dividing by Avogadro's number because they gave us molecules of water and they asked for moles of water, so we don't have to worry about atoms of hydrogen or whatever. So just particles to moles, divide by Avogadro's number. Okay. So if you don't know what IUPAC is, those are the people that come up with the rules for naming. So if they reference this on the SOL, don't worry about it. It's just, hey, name this compound the way we taught you how to name it. So remember, iron needs a Roman numeral. I don't know if your chemistry teacher uses the term mom ion, but if you're one of my students, you know what mom ion means. Iron's a mom ion, meaning it needs a Roman numeral. And remember, the Roman numeral represents the charge of the iron. So this would be iron Roman numeral 3 chloride because the iron is 3 plus. Now, how do I know the iron's 3 plus? I know the iron's 3 plus because it's paired up with chloride. And if we look at the periodic table, maybe I can look at the periodic table. Let's see. If I look at the periodic table, chloride, is it chloride or fluoride? Chloride, sorry. Chloride is a -1 ion, but according to the equation, you have 3 of them. So the total charge of 3 chlorides would be 3 minus, and since you have 1 iron, that means the iron would have to be 3 plus. It doesn't always work, but if you had to guess and you had no idea how to figure out what that Roman numeral was, a lot of times the subscript of the anion is the Roman numeral of the cation. That's not always the case, and I think there's an example coming forward where that isn't the case, maybe not. But if you had to roll the dice, I would say maybe a 60% chance that's going to work for you if you know you need a Roman numeral in your name. Okay. All right, so here we got a gas law, and what you have to remember about the gas laws is anytime you're plugging in a temperature value, it has to be the Kelvin temperature value. And so on the SOL, they're going to give you degrees Celsius most of the time, and you need to know, how do I turn this into Kelvin? All you have to do is add 273. So 25 plus 273, that's where that temperature came from, okay? 55 plus 273, that's where that temperature came from, okay? So the relationship between volume and temperature is a directly proportional relationship. So we're doing V1 over T1 equals V2 over T2, and the thing we're solving for here is V2, okay, the final volume. So we have the initial volume, 125 milliliters. We have the initial temperature, but we got to make sure we convert it to Kelvin. And then we have the final temperature, which we have to convert to Kelvin. So we would cross multiply. So it would end up being this times this, and then we would divide by 298, and that's where the 138 came from. Understand what to expect, right? Volume and temperature have a direct relationship. So if temperature goes up, volume should also go up. So since we increase the temperature, the new volume I solved for should be greater than 125. If I got an answer that was lower than 125, I know I did something wrong. Okay, because volume and temperature have a direct relationship. Right? But it's only on the Kelvin scale that it's a direct relationship, not the Celsius scale. So you got to make sure you convert to Kelvin. Okay. So if you see the term catalyst, just think to yourself, catalyst, you need to know two things about a catalyst: what it does and how it does it. So what it does, it speeds up the rate of a reaction. How does it do it? It lowers the activation energy. So you're looking for something where maybe they're talking about lowering the activation energy of the reaction, or they're talking about speeding up a reaction when you see the word catalyst. Okay, and that's our answer. Lowers the activation energy. Okay. It doesn't matter what biologists do with it. It's just catalyst speeds up a chemical reaction by lowering the activation energy. Okay. So here we got another mole map conversion, but it's a two-stepper. So we got grams of hydrogen, and they remind us that hydrogen is H2, and they tell you that it's at STP. Now, when you see STP, understand that STP means standard temperature and pressure. Okay, and it means on the SOL, if you see STP, it means, hey, you could probably use this conversion, 22.4 liters over 1 mole, or you might flip it and say 1 mole over 22.4 liters. Understand that STP does not mean 22.4. It means you can use, those are a set of conditions where you can use 22.4. Okay, so if we're using our mole map, or which you don't have, you'd have to write it down from memory on your scrap paper. They don't give you a mole map for the chemistry SOL. But we got to go grams to moles. So how do we do that? We divide by the molar mass. We figure out the molar mass of H2 by checking in on the periodic table. Hopefully you have hydrogen molar mass memorized by now. And H2 would be 2.02 because it's 1.01 plus 1.01. So hopefully you have that memorized by now because you've used it so much. If not, yikes. Okay. But we would take our grams and convert it to moles. And then once we have moles times 22.4 will give us liters. And again, we're allowed to use this conversion factor because we're at standard temperature and pressure. And 1 mole of any gas at standard temperature and pressure will occupy a volume of 22.4 liters. Okay. And so we end up with 398, and it's 399. And it's probably because when they did their calculation, they just probably divided by 2 instead of 2.02. Okay. But trust yourself, depending on how you round and how they round, your answer might not be exactly what an answer choice, but I mean, close enough. All right. So here's just balancing again. This one can be a little bit tricky, but let's go back and forth. I have 1 calcium here. I have 3 calciums here, so that's why I put a 3 here initially. Now I might change that later if I need to, but right there I'd put a 3. Let's look at nitrate. Don't look at nitrogen individually here and oxygen individually. Look at it as you have 2 nitrates. So nitrate is NO3, and this subscript is telling you have 2 of them. So you have 2 nitrates. But you put a 3 here. So since you put a 3 there, you really have 6 nitrates. So if you come to this side of the equation, you only have 1 nitrate. So that's why I put a 6 here. Now, we'll go to the next thing. I have 3 hydrogens, but because I put a 6 here, I have 6 hydrogens. So I put a 2 here to make this have 6 hydrogens on this side. And then putting a 2 there gave me 2 phosphates. And if I come to this side, I already have 2 phosphates, so I'm balanced. So 3, 2, 1, 6 would be our coefficients. And they want the coefficient of the phosphoric acid here, and then, so it's a 2. Okay. All right, increase the volume of a sealed container will cause the gas particles with the container to collide less often because they're in a bigger space. Okay, so remember, pressure and volume are inversely proportional. So if you increase the volume of your container, but you keep the temperature constant, then the particles will collide with the walls less frequently. And if you have less collisions with the walls, you'll have a lower pressure. Okay, so as volume increases, pressure decreases, and collisions would become less frequent. So one of the answers might have been collisions become less frequent, but not more frequent. Okay. So here we got melting points, group 1, group 2, group 3, group 4. We're told what the actual melting point is, and we want to know precision. Remember, this is kind of a distraction here. You don't need to know what the actual value is to determine if you're precise or not. You need to know the actual value to determine if you're accurate or not. So if they had asked about accuracy, we're trying to find the group that has the closest values to 113. But if they're talking about precision, they're just asking about which groups had the most similar results, which group data were close to each other. So if you look at group 4, their data didn't really vary that much, 110 and 111. So that's precision. Now, it might not be accurate, but if your values are close to each other, that's precision. It's when your values are close to the right answer, the true value, that's when you're accurate. Okay. So group 4 is the most precise because their data was in the most agreement with itself, okay, but not with the true value. Okay. All right, so consider any set of 3 adjacent elements on the periodic table. For which characteristic is the average of the 3 elements always equal to the value of the middle element? So adjacent means next to each other. So we're talking about, like here, boron, carbon, and nitrogen. Okay. Well, if I average their average, if I took the average of their atomic masses, that's not going to average to be 12.01. But if I took the average of their atomic numbers, 5 plus 6 plus 7 divided by 3 ends up being 6 because it's smack dab in the middle. Okay, so the answer is atomic number. Okay. And remember, atomic number is also number of protons, so maybe they could ask the same question, but the answer choice, instead of saying atomic number, is number of protons. I don't know. Be a way to adjust that question if they want to ask it again. Okay. So they give us the molecular formula, they ask for the empirical formula, so all we have to do is reduce the ratio here. So since we have a 2, a 4, a 10, and an 8, and they're all even numbers, we can divide each of these by 2, and then we get our lowest whole number ratio. So that's how we got that. Now remember, 1's understood, so I wrote 1 there, but notice the answer choice doesn't have it there. It's because it's understood. Okay. All right. Here, this is paper pencil, but like on the actual SOL, you'd be clicking and dragging the letters and the subscripts in here. So diboron means 2 borons, and trioxide means 3 oxygens. And just remember, the chemical symbols always start with a capital letter or uppercase letter. So boron isn't B lowercase, it's B uppercase. And oxygen isn't O lowercase, it's O uppercase. Okay, so B2 because it's diboron, and O3 because it's trioxide. Okay. All right. Name this ionic compound. Now remember, aluminum does not need a Roman numeral, right? The ones that need Roman numerals are usually the ones that are in this block. So these metals need Roman numerals. And then remember, these 2 metals, tin and lead, also need Roman numerals. Aluminum doesn't need it. All right. These metals over here, when you name them, don't need a Roman numeral. So aluminum doesn't need a Roman numeral. It is a metal. Iodine's a nonmetal. This is an ionic compound. All you have to do is name the cation, name the anion. The name of the cation is aluminum. It's not aluminum 3 because you don't need the Roman numeral. And you don't use prefixes for an ionic compound. Okay? So you don't say triiodide. You just say aluminum iodide. Okay? All right. How many moles of carbon dioxide are produced when 6 moles of butane react in excess oxygen? So our first stoichiometry problem, and all we would have to do is take 6 moles of butane, multiply it by 8, and then divide it by 2, multiply it by our mole ratio, and that would give us our answer. Okay, so 8 moles of CO2 for every 2 moles of butane. Doesn't matter if you reduce the ratio or not. You could multiply by 8 and divide by 2, or just multiply by 4 over 1. Multiplying by 4 over 1 will give you the same answer. Okay, so just stoichiometry. But everything's pretty much done for you except for the stoichiometric step, except for the mole ratio step, right? We have our balanced equation. The given amount was moles. So if it wasn't moles, we'd have to take the amount given and convert it to moles, but it was moles already, so then we can skip straight to the mole ratio step. Okay? All right. So we'll do one more, and then that'll be the end of part 2, and then we'll start part 3 with number 40. Okay. So which structure represents a nonpolar molecule? Remember, nonpolar means it's symmetrical. If it's asymmetrical, it's going to be polar. So this is not symmetrical. This is not symmetrical. This is clearly not symmetrical. This is symmetrical. It's nonpolar. Okay. And then remember, hydrocarbons we always say are nonpolar. And when you add functional groups, like here's an aldehyde functional group, here's a chloro functional group, here's an alcohol functional group. When you add functional groups to organic compounds, hydrocarbons, they're polar. If it's just carbon and hydrogen, nonpolar. Okay. All right. So that ends part 2 of the video. We'll start off part 3 and finish up the video series with questions 40 through 50 in part 3. All right.